So let's have a little lesson on nuclear reactions. I want to try to record this at home using an app that I haven't used in a long time. So let's see how it works. So nuclear reactions are reactions that involve the nuclei of the atom. And that's all we're really looking at. It's not the electrons and all the acid-base reactions and precipitation reactions. Those all, even though you can't see it yet, involve the electrons of the atoms. So in nuclear reactions, we need to see first of all what's different between them and chemical reactions. In chemical reactions, when you make the reaction take place, you're breaking and forming bonds. That's all that's going on there. But when a nuclear reaction takes place, you have elements being converted from one form to another. And so in a chemical reaction, you've got to make sure the number of atoms on either side of the reaction are the same. That is not true for nuclear reactions. So I already stated this, that only electrons are involved. But in a nuclear reaction, you can have protons and neutrons involved. And even though we're only dealing with the nucleus of the atom, there can be electrons generated out of that nucleus. Those are known as beta particles, and we'll talk about that in a little bit. Now, when chemical reactions take place, relatively small amounts of energy are required or released. So the heat given off by a Bunsen burner, for example, that's not a tremendous amount of energy, although it will burn you. In a nuclear reaction, it is a tremendous amount of energy. So, your nuclear explosions, energy running off of nuclear subs, when we get nuclear energy from reactor plants, this is a lot of energy out of a very small amount. So that's what's different between a chemical reaction and a nuclear reaction. Now, before we can fully talk about balancing nuclear reactions, we need to talk about what radioactivity is. Radioactivity is one type of nuclear reaction. There are many types, but it's the only one we're interested in right now. It is the spontaneous emission of particles, okay, and or just energy, which is what we call electromagnetic radiation, from the nucleus, and it's all due to an unstable nucleus of an isotope. So we will see that if you have a nucleus that's not stable, and certain ones are and aren't, which we won't get into, then it will spontaneously try to get towards a stable nucleus. All right, so that's what radioactivity is. It's one type of nuclear reaction. Now let's get over here and talk about what we're really interested in this video, and that is balancing nuclear reactions. Now we have to be able to kind of refresh our memory on a isotope, the way we write isotopes. So we see here, we remember that the top number that we see here is the mass number, and the bottom number is the atomic number. The atomic number is basically the nuclear charge. Nuclear charge. Okay, so it's a number of protons in that nucleus. And the top number is the number of protons and neutrons. So when you balance a chemical reaction, we have to make sure the atoms are the same on both sides. But when you balance a nuclear reaction, what we're going to make sure is balanced is the mass number and the atomic number. So those must balance out on each side. Before we start balancing them, we have to talk about the particles that we're going to run across as we balance these. So look through this list and let's talk through each one. So sometimes a proton might be emitted or involved in a nuclear reaction, and the way we would designate a proton is either with a P or with an H, because when you think about a hydrogen atom, it only has one proton. Excuse me. So you notice the top number, which is the number of protons plus neutrons. A proton certainly wouldn't have any neutrons, so its number up there is 1. One proton, no neutrons, and it's a 1. The next one we'll examine is a neutron. A neutron has no nuclear charge, so the bottom number is a 0. But the top number is the number of neutrons plus protons, and since it has one neutron and no protons, it would have a number 1 up there. Now this is a beta particle, and my slide did not translate this property. That should be a beta there. A beta particle is simply an electron. So we can use an E or we can use the beta symbol for it. The top number we know is the number of protons and neutrons. Well, an electron doesn't have either, so that top number is a 0. The bottom number, when you consider that it is the nuclear charge, should be a -1 sitting there. So you would no longer just think of this bottom number as the number of protons. We can think of it as its charge. And the number of protons of a nucleus is what gives us its charge. So that's what we always thought of that bottom number, which is Z as is the number of protons. But in nuclear chemistry, we should consider it instead the nuclear charge. So in a positron is a positively charged electron. So it still has no protons or neutrons. That top number is still 0, but now it carries a +1 charge. We usually put that +1 with it instead of just a 1, and that helps us to see it as a charge, not just the number of protons. The last one is an alpha particle, and once again it did not translate that alpha. This alpha particle is really just a helium nucleus, and so sometimes it's represented with an He or an alpha. Either one are correct. A helium nucleus has 2 protons and 2 neutrons. And so we have that top number of a 4 sitting there for our alpha particle. So you have to get yourself familiar with these particles as you work on balancing nuclear reactions. Okay, so now we're going to work on this one together. The answer is sitting right down here. We'll see how that comes about. What we do in balancing nuclear reactions is we make sure that the atomic number and the mass numbers are equal on both sides. So when we look at these bottom numbers, we see a 12 plus a 1. We see a total of a 13 for that atomic number of Z. It adds up to 13. So we have to make sure on this side they also add up to 13. So if the 2 is already there, what would have to sit here in order for there to have them add up to 13? Well, that would have to be an 11. So the bottom number is an 11. Now the top number is also much balanced, so we add up the 26 and the 1 and we have a 27. Over here, these two numbers have to add up to a 27 as well. We already have a 4 with the alpha particle, so that gives me a 23, because 23 plus 4 is 27. Now what about the X? That is, of course, the symbol for the particle here. And we get that by looking at this number 11. If you go to a periodic table and you find the atomic number of 11 on that periodic table, that's where you will see that it is a sodium. So that is a typical balancing of a nuclear reaction. It's not like balancing a chemical reaction. We will give you a particle that you're missing, and you will figure out what it is by knowing that the atomic numbers on both sides and the mass numbers on both sides have to add up to the same value. So now you're going to try one. Okay, so let's see if we can find my, where did it go? There it is. The one you're going to try is this guy. Okay, so here's the nuclear reaction. And this is A, this is B, this is C, and this is D. Okay? So you're going to look at this reaction and determine which one of these is the correct answer. Well, hopefully you came up with A. Okay, if you did not come up with A, let's see how we got that. It's really easy to mess up the bottom number. These two numbers have to add up together to give you 19. And it's easy for you to look at it quickly and say, well, it has to be 18. But 18 plus a negative 1 doesn't add up to 19. The bottom number has to be a 20 because 20 plus a negative 1 adds up to 19. And then, of course, the top number would have to be 40. And then you look at a periodic table and you say, well, what element has the atomic number of 20? And that is calcium. So that's how you balance nuclear reactions. In terms of the process, it is not very difficult.